So yeah, welcome everybody. I am Nate Corderer. I am the education director at Earth Lab and at ESOL. And I'm excited to welcome everybody to the EDS seminar today. We're going to hear from a handful of students who participated in our Earth Data Analytics Professional Graduate Certificate Program over the course of the last school year. I'm going to say a few words about the certificate program just to give a plug at the top here. So you have a little bit of context, and then I'll turn it over to the course instructor for this summer, Dr. Lily Jones. She'll have a few words, and then she'll hand it off to the students for the presentations. So that's what you're all here to listen for. You heard me mention that the presentations today are part of the bigger Earth Data Analytics Professional Graduate Certificate Program. This is a 3-course, 9-credit professional certificate that we offer through the continuing education school here at CU, as well as the Department of Geography. And so I've got on this slide here just kind of a breakdown of some of the topics that we teach over the course of the over the course of the 3 classes. You can see the course number at the top of each one of these kind of sections that corresponds to the course catalog number in geography for each one of these. In the fall, we teach an Earth Data Analytics Bootcamp course that really gets folks interested in we started working with different open data science tools, including GitHub and Python. We teach a number of different Python libraries that get folks involved working with different time series data applications, as well as different spatial data products, including vector data, raster data. We teach content and topics like how to do more advanced things like working with loops and conditional statements and functions. In the spring semester, students come back and it's a little bit more advanced. We teach them how to work with some more advanced data products, including multispectral data, NDVI. We teach people how to access data through APIs and from the cloud. And in the spring semester, students also start brainstorming and planning for their applied projects, which you're going to hear more about here in just a few minutes. Then in the summer, students come back and they're just finishing this up now. They've had the summer and part of the spring semester to work on an applied project. So during the summer, they build a GitHub repository for this project. We talk a little bit about best practices with data science management. We hit some things about science communication. In years past, I know that we've had students write a blog post about their work, and then they do a final presentation, which is what you're here for today. The courses are currently taught by Dr. Catherine Siegel, who is an associate professor in the geography department, as well as Dr. Lily Jones, who is on the education team here at Earth Lab and at ESOL, and who you'll hear from in just a second. For those of you that are on the call that would be interested in learning more about the certificate program, if you're interested in learning more about the certificate program, I've got this QR code up here on the screen here. You can see that there's some of the information at the bottom that kind of repeats what I just said here. But, you know, if you're interested in learning skills to become a data scientist or a geospatial analyst, or to learn how to do things that a GIS technician might do, but with open science tools, this is a program for you. And so please feel free to shoot that QR code with your phone if you're interested in learning more about that. The other thing that I'll mention too is, I know this is short notice, but tomorrow from 4 to 5 p.m. on Zoom, Lily and I will be hosting a virtual Q&A session. If anybody would like to register for that, the QR code with the little dinosaur in the middle at the top is for you. And yeah, we'll be meeting tomorrow for an hour in the afternoon. This session will get recorded and we can share that with you if you're interested in hearing more about what we have to say about the certificate program. Lily, did I miss anything? Okay, perfect. I'm going to stop talking now and I'm going to pass it off to my colleague, Dr. Lily Jones, who's been working with these fine students over the last 10 weeks or so, I guess, as part of the summer semester. She's going to give you a little bit more background about what they'll talk about, and then we'll pass it over to them. So thank you, Lily.
Hi, everybody, and thanks for joining us today. I've actually been working with this cohort of students for the past year, as I was the assistant instructor for Dr. Catherine Siegel. And it's been a very rewarding experience. This is an incredible cohort of students, and they have some very interesting projects to present to you today. They've been working hard to develop their skills in Python coding in geospatial workflows and geospatial data science, in working with project partners, and in communicating science. So with that, I would like to introduce our first presenters, Dr. Kaylee Ward, Max Warnock, and Nate Hofford, who will be presenting their project over the Pawnee National Grasslands Land Swap Optimization.
I'll advance the slide if you want to start off.
Sure. So for our project, yeah, we're working on identifying high impact land swaps for the Pawnee National Grasslands, which are in northeastern Colorado. And this is our team. We have 3 people, Kaylee, who's been working on the land swap app, which you'll see in a minute, which is looking really, really nice. And then Nate and I have been working on the land swap metrics and kind of algorithm that goes behind how we pick land swaps. And then this is our project partner, Grasslands Unlimited. And we've been working a lot with them on their goal. They really wanted us to help them find a way to identify the best land swaps to kind of maximize contiguity of federally owned land in the grasslands. Does Kaylee want to?
Yes, and then hopefully you can hear me. This is just some images of what the grassland looks in this area, both on the western and eastern Pawnee.
And then this is just a map of the land ownership types of the grasslands. So we have 2 sections, a western and eastern portion. And within that, we have federal land in the green and state land in the blue. And as you can see, it's a real patchwork of like fragmented land. And that's partly because I think during the Dust Bowl of the 1930s, farmers were selling their land and to the government, and so that's why it's all fragmented. So the goal of the project is to try to maximize the contiguity, especially of the federal land, through land swaps. And there's a picture from Nate's of just an example of how fragmented habitat can lead to non-uniform land management. So here's some nice grass and then some grazed area, which is what we want to try to minimize.
Cool. So as Max was talking about, we're trying to maximize contiguity. So what actually is contiguity? You can see here, the dark green patch, each one of those smaller squares is a parcel and the larger green is a patch. So each one of those is an individual land ownership parcel. We considered contiguous area if 2 parcels shared an edge. So in this example, for this 1 kilometer parcel, we would have a contiguous area of 4 kilometers, and this would be a not contiguous section because it touches by a corner. So we'd have 4 kilometers of contiguous area for this patch here. We also were curious about exposure. So from that picture that Max showed, you could see that there's like a like brown area and a green area in that grassland. So that's because one landowner is doing certain management and another owner is doing different management. And so you can expect that, like in this example where there's orange non-federal patches, they might be doing different land management. Whereas on the federal patch in green, they're doing other land management. And so the exposure or the perimeter of the area that is exposed to non-federal land matters because you can't manage land that you don't know. We calculated the exposure for all of our different patches. So these in red here is exposed edge. In green is interior edges. So those are controlled by the federal government. We can calculate an exposure score. And in this case, it's 80% or about 8 kilometers of exposed edge.
Right, so then once we had those, we needed to identify some swaps. So we had to identify some release parcels. So that's like federal land that imagine you already have the federal land or something. You want to find the parcels that are like on the very edge. They're not very contained. They're far away. We want to swap those out for something better, right? So we have a whole bunch of criteria that helps us identify those ones that are not as valuable for making a contiguous block of federal land. And then we acquire parcels that we want to acquire, and they need to touch the federal land, and they're either like state or privately owned. So we have a lot of criteria to help us find those types of parcels. And then once we have those, we need to rank our acquire and swap, or acquire and release parcels, right? So we decided that bridge swaps, where we acquire a parcel that connects to federal patches, is one of the best ways to improve contiguity. Acquiring that bridge is really valuable. So we rank that highest in our algorithm. And then, but not all bridge swaps are created equal. So there's some bridges that are wider and help us more than like a narrow bridge that is not as beneficial for the ecosystem. So we rank those higher. And then we also look at patches or bridges, acquiring bridges that connect bigger patches rather than connecting like two smaller patches. We rank bridges that connect the two bigger patches higher. And then
Okay, so then on the exposure front, so again, we're trying to minimize the amount of exposure of federal land to non-federal land. So in this hypothetical example, you can see there's two possible acquire candidates here in light green. So these two light green squares are two different ways that we could increase federal land contiguity for this patch. This example would lead to 74% exposure of the final patch. And you can see that here. So it adds a parcel here on the edge that has 3 exposed sides. So you can see that would increase the exposure of that patch. Whereas if we were to acquire this light green parcel in the middle here, we're able to reduce the patch exposure to 59% or only 10 kilometers of exposure. So in this case, we would rank this swap higher than the swap on the left. In the event that we have like a tie between patch contiguity gain and patch exposure decrease, we can actually look at the specific parcels being released. So in light green here is our acquire parcel. So we're looking to acquire this light green parcel. And in red, we have 2 release parcels. So these are 2 possible candidates that we could swap for this green candidate here. The one on the bottom has 2 sides of exposure, and the one on the top has 3 sides of exposure. So in this case, we would opt to swap the 3 sides of exposure because that individual parcel has more exposure than the other parcel we could swap. Okay, and now I'll turn it over to Kaylee for this video of our actual tool. Kaylee, do you want to say anything before I play this? Or are you good?
I was just gonna say my lights just came back on. Huzzah. So this is like a 4-minute and 30-second demo of the tool, and I will put a link to the tool in the chat. So if anyone wants to play with it, feel free. Hello everyone, I'm going to give us a quick demo of our Land Swap Explorer. When you first come onto the Explorer, you'll be greeted by our information box on how to use the map, which tells you that green parcels are acquisition candidates and red parcels are federal release candidates. And you can see this legend down here as well in the swap view legend. You'll also see that we list the different filters available, and you can see those filters in the left pane here. You'll also see that we have a link to our project wiki, and if you open that, it'll give you more detailed information about how this Explorer works and some of the things that Max and Nate explained earlier. You can also see more information on our different filtering options, which we'll go over in just a moment. And you can also see that ranking hierarchy we went over earlier in the presentation. Now, when you're looking at the Explorer, you'll see that there's these 4 cards at the top of the map. And these are dynamic cards that will update based on your filtering parameters. Now, because our project partner only has a limited number of swaps that they can consider, we defaulted to the Explorer showing 5. And you can change this to whatever you like. But for these possible proposals, there's 1 acquisition parcel and 5 possible releases. And because we are essentially bridging 2 patches, right now the max possible gain of contiguous acres is going to be that of the smaller patch being connected, so 14,000 or so acres in this case. And you can see the top proposal automatically selected in the map below. And so you can see the bigger patch on the right and the smaller patch on the left. And if you zoom in further, you can see those release candidates, those 5 release candidates and the 1 acquisition candidate. You can also click on these different parcels and find out information about them, like their parcel number, if it's federal, state, or private, how big it is, its value, what its value per acre is, and how many proposals this particular parcel is in. You can do this also for the acquisition candidate. In this case, it's a private acquisition. It tells you who the owner is and that same information. Now, if you're just looking at the map here, one thing I would recommend is actually viewing all proposals, so it's just more fun to look at. And you'll see that our map automatically updates to all possible proposals, and you'll see that our cards have also updated. Very quickly, if we go through the filter options, you can look at acquisition candidates that are only state acquisitions, which of course is going to filter out quite a lot. You can look at private only acquisitions, of which there's more options. You can look at the swap type, so you can look at potential swaps that are only within the same federal patch or that are across different federal patches. You can also choose to only look at proposals of a particular patch. So we're going to use patch 6. This is our little cactus patch friend that we like, and you can see all of the release candidates and all of the acquire candidates. And you also see that the 4 cards at the top update based on what we're looking at. So I'm going to get rid of patch 6 here so we can look at everything again. And now we can also toggle on some different options. So if we are looking at federal contiguity, we can also try to make whatever release or acquire parcel also benefiting state contiguity and private contiguity of land. So you can toggle these on and off and see proposals that match those parameters and also do private. And because we don't necessarily want to swap parcels that have active oil and gas, we created toggles for both acquire and release parcels that have oil and gas to remove them from the proposal list. If you're looking at the bigger map here, you can show bridge swaps only, and it's going to limit what you're looking at. You can also look at the map in terms of the value, so that acreage metric. You can also change things by the exposure reduction score that Max and Nate talked about earlier. You can also do it by difference in acre size of the parcels and how far apart the parcels are. Now, the fun thing is when you do any sort of filtering, you can go down to the bottom here and see all of those ranked proposals, and you can pick whichever one your heart desires. So I'm going to pick 5 here. This is a cross-patch option, and it's going to automatically take you to where that is and highlight the different options. The nice thing is now that in the selected proposal pane, you can see this particular proposal and learn more about the different metrics, about the 2 particular parcels being involved, and everything else. We've also put the ranking information right next to the selected proposal so that users could easily see the ranking metrics and how that affects what you're seeing in the selected proposal or what those things mean. But you can essentially change anything and everything that you want, and this ranked list will change, and the top 4 panels will change, and so you're easily able to compare different swap candidates. So happy swapping, and let us know how you like it.
Anybody have questions for Nate and Kaylee and Max? Can I ask one? So what did the partner think of all of this? The person, the organization that you were working with, like what's been their feedback or takeaway?
Oh, yeah, you really loved it, I think.
Yeah.
This was, I think he said it was exactly what he was looking for. So he to help make proposals for swaps with the US Forest Service. So hopefully this could result in some actual real world change.
Yeah.
Virginia, is this translation?
This is your translation.
Your translation. Okay. Gotcha. Cool. Anybody else want to ask a question? Anybody online asking questions? Give it up for this group. Great job.
Is someone online going next? So change the.
Does anyone want to go next?
Yeah, I can go. I just have to enter the oh, no, you can keep recording. Also, I apologize. I have the wrong room number.
Say, I gave it wrong. I apologize.
Presenting from your own computer?
Yeah, I did turn in the PDF of my presentation. I was just not sure how well that would translate.
All right. Or you could, I can give you Rachel's email address if you want to email it to Rachel about it.
Yeah, I can do that. Yeah.
Yeah,
Mhm.
okay.
Thank you, Pawnee Grasslands Group. That was an amazing project. I really was impressed with how they worked with their project partner, who was a nonprofit called Grasslands Unlimited, that reached out to us last fall and said, hey, I have something I want to do, but I have no idea how to do it. Do you have anyone in your lab that might want to work on this project? And so we connected them with this group of students that were very interested in their work. And we do that generally in the spring in our second course. We have project partners, potential project partners come in and pitch their ideas to our students. And, students are, of course, always free to come up with their own ideas too. But if you are a potential project partner and you'd like to reach out to us, if you have, any research or project needs, we can, certainly tend to offer you some space to pitch your project to our students. We're just getting set up for the next student here. Happy to introduce Lynn Grace. She has worked on a project on the Nisqually watershed in Washington State, and she has produced a fuzzy logic model of that watershed to communicate and use as a screening tool. So Nim, whenever you're ready, go ahead and take it away.
All right, rainfall to risk, mapping surface runoff susceptibility under projected climate change scenarios in the Nisqually River watershed. And big shout out to Lily, who served as my science mentor towards this and answered a lot of questions I had throughout the process. I'm excited to share with you also a couple of goals of this analysis was to look at where is surface runoff susceptibility the highest in the Nisqually watershed historically, and does projected climate change increases, so we think that we will see increases in wet season precipitation in a lot of areas in the Pacific Northwest, and would that cause that susceptibility to shift on a map? I wanted to create susceptibility maps at the watershed level that could be used as a risk screening tool. And so why excessive surface runoff? Because it has real impacts. And so surface runoff can lead to flooding, which causes human safety issues as well as damage. Excessive runoff can reduce groundwater recharge. It increases water pollution and habitat loss, as well as lead to erosions and landslides. So why map runoff risk? So why, those are the issues of excessive runoff. Why can we map the susceptibility and why should we? So if we actually have a susceptibility map that we can use as a screening tool, we can focus limited resources, which means, a lot of places right now have limited budgets, limited resources. We can target investment where risk is the highest. We can also be proactive rather than reactive, so we can anticipate problems before they occur, identifying where infrastructure is needed the most, where our aging infrastructure might not be adequate to serve those projected climate scenarios. And this allows us to plan for a changing future and build climate resilient infrastructures and communities. And so why a screening tool? So why pick fuzzy logic? Full-scale hydrologic models can be very hungry for data, time, as well as resources. And this is not a replacement for those models, but instead a complementary watershed scale assessment and screening tool. This really supports vulnerable and high-risk communities that may not have access to those resources and be able to do that first pass assessment to perhaps target more localized, smaller scale studies that there may be the resources to do. But this screening tool can serve as a way to see where susceptibility might be the highest and do we see that changing in climate change scenarios in a relatively less computationally expensive way. And so how the fuzzy logic model works, so I had inputs, topography, landscape, and climate data, harmonized all together, and only the climate variables were changing, so keeping the landscape constant. Fuzzy logic model, so that scores each pixel on a runoff susceptibility score from 0 to 1, rather than forcing a binary yes or no. This allows for nuance. It allows multiple variables to compound and to weigh how much surface runoff susceptibility is. The outputs were susceptibility maps, historical, 1976 to 2005. A future map I did mid-century futures so that we see the climate change projections, but it's still near enough term that planning or decision making can be relevant to where we're currently at, as well as a change map to look at the changes. So here was the study area. We have the Nisqually watershed in Washington. It originates at Mount Rainier, which is an active volcano. You can see there on the map, and it flows 70 miles from the Nisqually Glacier to the Puget Sound across many different types of land covers and elevation, making it a very interesting study case to look at. So before combining it into our final susceptibility model, this was a key modeling choice that was made. And so runoff concentration was looked at and runoff generation variables were looked at separately before combining them into the final model. Runoff concentration to see where the drainage networks are, where flow accumulation and slope have impact, and the historical runoff generation combining the other landscape variables like soils and impervious with precipitation data. This, while still operating at the screening tool level, has more, more closely related to the hydrologic processes that actually occur. So I modeled those separately before going into the final susceptibility models. And this is where I'm really excited to share the results. So we have on the left the historical runoff susceptibility model, and on the right we have the future. Just looking at, eyeballing it, they do look roughly similar. We see in that kind of central watershed where risk is the highest, where we see the most runoff susceptibility. And we see, as it goes down, the places where we see the highest rates of change is the places that are moderately susceptible, and then the high risk also increasing as well. So overall, 69% of the valid pixels in the watershed did show some change, and 93% of those changes were increases. And while those increases were large increases, we did see those increases happening across the watershed, showing the importance of why making sure infrastructure upgrades are adequate, making sure high-risk areas, so areas that are already prone to flooding or excessive runoff, is only going to increase in that way, and showing that instead of shifting the susceptibility on the map, making new hotspots, we see an exacerbation and an intensification from climate change of already vulnerable areas. Also showing the need for this sort of screening tool. And so what are some of the next steps that I see for this? To validate the model against observed runoff and flood data. I would love to do a machine learning comparison and validation using random forest or a similar model. Adding more climate scenarios or models. So I use the 4.5, looking at higher emission scenarios. I also used the ensemble mean for the watershed for the model, but incorporating other projections and seeing how that might shift runoff susceptibility, and then applying this same workflow to other watersheds. And so that was my project here, building a fuzzy logic geospatial model to look at runoff susceptibility. I had a lot of fun doing it. Thank you. And here is my GitHub and my data citations. Any questions?
Nim, can you put a link to your GitHub in the chat too?
Yes, I can.
Thank you, Nim.
Great job, Nim.
Anyone have any questions for Nim? Yes.
Does the area that has the highest increase in like runoff susceptibility for projections, does that correspond to areas of like a lot of infrastructure and roads and?
Not exclusively, no. So there are, towards the mouth of the river on the northwest side of the map, there was a higher increase. And that is an urban area, but it wasn't exclusively where we saw. So in the central, mid-central part of the map, there was the highest increase. And that's actually, there are less, the soils, so when I was looking at the soils in that area, have less infiltration as far as hydrologic soil group. And so that seemed to have a big factor. I played with different gamma values in the testing process, and the soils did seem to have quite a lot of influence over that. And then there was some of the urban areas, but it wasn't exclusively tied to urban areas, which I thought was interesting.
Any other questions for Nim? Oh, great. Let's give her another hand.
And this works, yeah, right? Right. Hello, everyone. My name is Livian Von Dran, and I am an entomologist for the Spring Institute for Forests on the Moon. So, the Plant Bee CubeSat Terrarium project is an initiative by the Spring Institute to send a self-sustaining terrarium into low Earth orbit for 2 to 5 years. And the significance of this project is that it will grant us insight into the ecological functioning of biological space life support systems that are going to be necessary to sustainably replenish life-sustaining resources for space settlements. These are the species I'm going to be I used in the terrarium simulation. And there were a few goals I had in mind for this project. I wanted to determine the bodily elemental composition of the free terrarium species I chose, as well as determining carbon and nitrogen soil concentrations in their area of overlapping habitat. And I also, the long-term end project of this or end goal of this project rather, was to be able to simulate the carbon and nitrogen cycles in this terrarium ecosystem. These are the data sources I used. And to be able to accurately parse the soil nutrient concentrations in their habitat, I first had to identify an area of habitat overlap. And to do so, what I did is I used the Global Biodiversity Information Facility database, and I mapped observations of the free species onto an interactive map. And from there, I was able to find a suitable area of habitat overlap near the German-Polish-Czech border. And from there, I used the I sent to get the soil nutrient concentrations for that overlap area. What I did is I sent in a request to the European Soil Data Center, and specifically, I requested access to their Lucas 2018 topsoil data set. And just from there, it couldn't be downloaded with a function, so that had to be manually downloaded. But from there, I was able to find an appropriate soil sample. And just on the bottom right here, you can see the soil nutrient concentrations here. And it had a carbon nitrogen ratio of approximately 10 to 1. And what this implies is it's a moderately fertile nitrogen rich soil system where decomposition is going to take place relatively rapidly. And this is an ideal environment for the chosen moss species. So to determine the elemental composition for the target species, I manually downloaded the Stoic Life data set, and I filtered the data frame for closely related species to extract their carbon and nitrogen percentages by their dry mass. And this is kind of a common issue in ecological stoichiometry, where data is not necessarily going to be present for your specific target species. So you have to subset with either just generalized values for a specific organism group, or you have to just try to find as closely a related species as possible. So these are my final simulation results. What you can tell from here is this was after the first thing I did is I plotted the population growth rate for the two invertebrates. And then I used that information and supplemented literature values to just obtain this final simulation. So probably the main thing you're going to notice about those simulation results is the carbon pool for the MOS system is relatively large, so that definitely needs to be adjusted because moss species, they cannot continuously absorb carbon. There is a cap to what they can absorb, and brain fart for a second. And there's not a lot of literature information about the specific cap for Physicometrium potens. But what you are also going to notice is this represents, I believe that is going to be the carbon levels for the detritus pool, and that does seem to be one of the primary limiting factors, because that value is going to drop below 0 over time, which that's technically not biologically possible. But what it does indicate is that the current setup as is would run out of the carbon for the decomposing leaf litter. So I believe the solution to this is implementing biomass growth of the moss into the model, and that should hopefully resolve that issue. But currently, as is, the terrarium ecosystem would not be self-sufficient if it truly is as mapped out. But I think to definitively answer that, I need to make those biomass adjustments. And for next steps, I originally wanted to also map phosphorus and potassium cycles for the terrarium ecosystem, but I unfortunately was not able to find the percent dry mass data I needed for these two elements. So I settled for doing carbon and nitrogen cycles for now. Additionally, I want to access ESDAC's soil biodiversity DNA bacteria and fungi database, so I can better incorporate soil microdata into the final simulation. And lastly, I want to figure out how to model the impacts of the low Earth orbit environment on the nutrient cycles, because with that environment, there's going to be two main constraining factors. There's going to be microgravity, and the organisms are also going to be subject to essentially rapidly shifting photoperiods, where it's going to be 60 periods of light and 30 minutes of darkness. And that is anticipated to negatively impact the circadian rhythms of those three species. Does anyone have any questions?
It's like all of the species in your simulation were starting from like 0 almost. Are you anticipating setting like a limit of like you have this much moss to start and this many insects?
Yeah, so the starting population for I can't recall the it doesn't actually start from 0. It's just, I suppose, with the way it's laid out, it appears that way. So for this simulation, for the isopods I'm using, I set the starting population to 15. And for the springtails I used, I set the starting population to 50 individuals. And I also implemented placeholder carrying capacity values. Those still need to be fully determined, but the reason it the values seem so minuscule is that it's the terrarium is only I think it's only 0.7 liters. So the total biomass values you are dealing with are essentially going to be very minuscule.
Another round of applause.
Thank you.
Next up, we have Charlie Caravati, and he is working on something very interesting. He's interested in LiDAR, and he's working on a lightweight Python workflow to detect mirrored surfaces in LiDAR point clouds for interior LiDAR viewing, which might sound a little convoluted, but basically if you use a 3D camera inside and you have a reflective surface, that can produce data artifacts in your data. So Charlie's working on a way to deal with that. So
Yes, it's a mouthful, but we are going to break it down and go through it. So thank you very much. My name is Charlie Caravati. I am working towards my master's in applied mathematics at CU Boulder with a focus on spatial analytics and statistics. This summer, I'm working with Prolog Hospitality in Richmond, Virginia, using LiDAR scanning to create digital twins for hospitality, construction, architecture, and engineering projects. This type of reality capture generates highly accurate point clouds of physical spaces. This is a hotel room, but requires a number of processing steps before actionable models and maps can be used. My project is working towards automating the tedious requirement of manipulating and manually clipping point clouds to remove bad data generated by mirrors and reflective windows in mobile LiDAR data, some of which you can see here, but I will highlight as we get further along. Compared to static scanners, which take individual scans from a fixed point, mobile scanners utilize backpacks or wheels to continually capture spatial data. In both cases, LiDAR scanning measures the angle of release and time to return for millions of laser pulses a second. This works exceptionally well on most surfaces, which scatter the laser in all directions, including back to the sensor, and vector math helps plot that point in a virtual space that corresponds very closely to reality. Mirrors and highly polished smooth surfaces, however, preserve the angle of the full laser pulse and reflect it back out into the room where it eventually scatters on a typically rough surface. And when enough of that scattered laser takes the exact reverse trajectory back to the mirror and then the sensor, the change in direction is not recognized and the point is placed on the other side of the mirror as if it traveled through a portal. I have a very basic sort of diagram trying to explain some of how this happens, but the scanner captures both the real object and the fake object, which you can start to see. Here's the real bed, and then there's sort of a reflected bed through the mirror right here. In order to programmatically identify ghost points that appear to travel through In order to programmatically identify ghost points that appear to travel through walls, I first need to identify the walls themselves. To accomplish this, I repeatedly run an algorithm to calculate the equation for a plane between three random points, and then check the orientation and density. Dense vertical planes of a large enough size are most likely walls, and I can tweak the parameters of the algorithm to be more or less sensitive to various factors and help establish a floor plan. The walls next pass through another set of code to flatten and classify individual gaps as doors to be left open or mirrors to be filled in, which you can see some of these spaces are filled in and some are left open as green spaces for the doors. Because windows and mirrors show up as empty space on the wall, patching these gaps is crucial for testing potential violations where a laser measurement appears to travel through the mirror frame. By testing and adjusting physical characteristics unique to doors, I can leave the doors as true gaps in walls while filling in the spaces left by mirrors and windows. The key logic behind ghost classification relies on connecting each point in the cloud to the scanner at the time of capture and then checking if any walls have been intersected. Unfortunately, just for this context, mobile scanning captures the same points repeatedly and keeps more or less the best measurement, so there's no timestamp or scanner location information included with every point. Instead, I can use location data for each time the scanner was used to take a panoramic photo and connect the dots for a trajectory path, which you can see here. By looking at the shortest distance between each point in the cloud and the trajectory line, we can get a solid estimate for ghost points, and filtering for intensity and proximity to walls helps avoid false positives. I'm currently testing a number of various point clouds and interior environments through the workflow to see if consistent parameters can be established, which is currently in process. The reinforcement learning and trading data for wall detection and gap classification could increase accuracy, but might increase implementation complexity and processing speed beyond practical limits. Point clouds contain massive amounts of data, and processing quickly becomes a real strength. My hope is to refine this lightweight workflow sufficiently to provide production benefits in recognizable situations without attempting to solve the entire problem scenario. The workflow is currently set up for standard format mobile point clouds and visualization to see how different parameters affect various stages in the algorithm. As I am still testing the effectiveness, I have not built out full exporting of classifications into the workflow, but that would be the next immediate step once results are satisfactory. I'm also planning to implement a similar workflow for static scan data, which does contain true trajectory data, but introduces new challenges of its own. And I have included a link to the blog and repository, which contains more detailed information on the algorithm and the whole process. Thank you.
Great job, Charlie. Charlie, can you put a link to your GitHub portfolio in the chat too?
Absolutely.
Folks on the call that are interested in learning more about the certificate and wanted to see some examples of some of the student work. And so thank you, Nim, and thank you, Charlie, for adding your GitHub. Vivian, if you can share your GitHub link too as well, and Nate and Max and Kaylee, we just want to show off those portfolios because they're like a great way to advertise the program and to show off all the cool work that you're doing.
Hi, my name is Allison Gregory, and I'm sorry I couldn't be with you in person today, but I have learned so much in the certificate program about how easy it is to use really cool coding techniques and apply them to complicated processes. So in my current job, I work with numerical weather prediction modelers and software developers who create our nation's operational forecasts. So in this project, I just wanted to create something for them to easily explain their work to younger generations, to students, and to the general public. So to get the weather forecast that you see every day, the National Oceanic and Atmospheric Administration, or NOAA, and the National Weather Service have to run these complex numerical models through giant supercomputers. And for this work to be successful, scientists need to be able to log onto these high-performance computers, usually with special credentials, and they also often need to understand multiple coding languages like Fortran, Python, and shell scripting. And to modify these models, they need a comprehensive understanding of physics equations that govern the way air and moisture moves through our atmosphere. So there's a lot to understand if you want to know how we get our daily weather reports. So the goal of this project is to teach how real forecasters and weather modelers work through an easy to understand Python notebook. So this will also hopefully bridge the gap between technical scientists and students. It will also show you how forecasters make the maps that we see every day. So this project pulls real weather model data and visualizes a gridded data set. It'll also use loops, tests, and have clean code to optimize the workflow. And it'll connect to an actual storm that happened in 2020. So this is the overview of the Python notebook that we'll be looking at. It follows the coding format that we learned in class. And of course, a lot of setup goes into these Python notebooks, but this is the most important package that I'll be using in this presentation. It allows us to download and work with numerical weather prediction data. So we'll be looking at the high resolution rapid refresh data set, but there is potential for a lot of analysis here. You see there's a lot of other models we could be looking at. So the case study we'll be looking at is in Cedar Rapids, Iowa in August 2020. A derecho occurred in that area, and that's a severe windstorm that can have gusts up to 75 miles per hour. This one in particular did $11.2 million in damages. So it's still one of the costliest US storms on record, and people like to study it a lot. So to collect the data, I used a function to get the forecast run at each hour time step during a 24-hour peak wind period. In this case, we'll be looking at winds, but I just wanted to show you that when you download this whole gridded data set, there are also other variables we could look at, like temperature, humidity, precipitation, and snow. So interpreting the data, we see that the forecast provided on the morning of the storm, sometimes it over forecasts and sometimes it under forecast. The orange line is the forecast from the morning that the storm occurred, and then the blue line is the analysis of the data after the storm had already passed. So this notebook also allows you to visualize the data, and so this image is just one example of how you can look at the wind speeds over the area of focus. The next steps are to share this work with the existing users and stakeholders to get some feedback. I'm also curious how this work fits in with other tutorials and projects. Most interestingly, we are planning to launch a weather camp where students can run their own weather forecasts and see how it aligns with the weather they're experiencing. So in conclusion, this project revealed that it is possible to interpret and visualize numerical weather model data without a high-performance computer or with any specialized skills or credentials. We can use this as an opportunity to teach students and the general public about how national forecast models work and how we predict our weather every day. So big thank you to everyone who helped me out during this program. And all the other people working on derechos and weather research in general. I truly learned so much, and I'm so excited to put these skills to work.
Hi, my name is Max Deswein, and I would like to present you the current status of my project, Machine Learning Approaches for Equivalent Latitude Estimation. So what is equivalent latitude? It is a quasi-Lagrangian perspective of the atmosphere where we follow air masses with the same dynamic history. Instead of using geographic latitude, we use potential vorticity as a coordinate. On isentropic surfaces, the area of each PV contour is centered on the pole and its latitude is determined. The benefit is a less artificial variability and is a common tool in stratospheric research. I want to address two questions in this status. The first one is, what is the best method for calculating equivalent latitude, and to what extent does it depend on the real-life product? For this, I would like to compare two different PV equivalent latitude calculations. The first one is the classic piecewise method, where PV is considered constant within each grid cell, and the other one is a contour-based region of interest method, where PV is interpolated within each grid cell. Furthermore, I would like to look into two different realized products, error 5 and error 2, and see where the difference are for equivalent latitude regarding these products, and what other applications with MLS ozone data. The second question is, can machine learning approaches lead to comparable results? For this, I would like to see whether two different machine learning models can work. The first one is the convolution neural network, CNN, or the physics information neural network, PINN, and see whether they can create comparable equivalent latitude estimation along radius zones. And these models are trained on the PV-based equivalent latitude from the question 1. This is a quick overview of the data which are used. As I said, we look at two different realized products, error 5 and error 2, with slightly different resolution. Error 5 comes in at 0.25 by 0.25 in our resolution, and error 2 comes in at 0.5 and 0.625 and 3-hour resolution. There's slightly different assimilation methods. For the time period from 2023 to 2024, we look at 12 UTC PV fields from 300 to 1400 Kelvin, and for some selected days, we look at the full day PV fields. In addition, we also look at some observations for testing. These includes MLS ozone and temperature data because they have a daily global coverage. We use NOAA Aircore N2O profiles and NOAA ozone zones profiles from Boulder, Colorado. And at a later stage, we like to include the climate indices like the QBO phase or endo state. The first results are for the method comparison. For this, we look at two analytic PV fields and one high-resolution PV field, for which we get exact equivalent latitude values. The top row of the left plot shows from left to right a zonal field, a wavy field, and a wavy field with cutoffs. The bottom row shows the difference of the calculated equivalent latitude to the exact values. Especially for the wavy and wavy plus cutoff fields, the piecewise method shows better results, whereas the region of interest method shows a systematic bias in both hemispheres. But as the grid size resolution becomes higher, the differences become smaller between these methods, but still with better results for the piecewise method. In the next step, we compare the two linear products, error 5 and error 2. Here we see the root mean square deviation of error 5 and error 2 equal latitude for different seasons, isentropic levels, and by latitude ranges on both hemispheres, and this average over 3 years. What we see here is that below around 500 Kelvin, there's generally larger deviation between these two Renals products, and above slightly smaller, in between like 2 to 8 degrees. The maximum deviation occurs in the summer hemisphere at high latitudes, where the polar vortex is not existing and the PV gradients are very flat, so small PV differences can cause larger equilatitude differences here. As said in the beginning, we assume that equilatitude reduces the variability when we look at, for example, zonal means of ozone, so it make it more compact. This we try to do with a case study here. We looked at MLS data and did the zonal mean in equilatitude and geographical latitude in top row for error 5 equilatitude and in the bottom row for error 2 equilatitude. What we see here now is that where it's blue, we've got a better result in equilatitude, and where it's in red, we see a worse result in equilatitude. So it really helps in winter hemisphere, where the PV contours indicate true mixing barriers, for example, the vortex edge, whereas in the summer hemisphere, we see a larger variability, so it makes it worse, I would say. In the summer lower stratosphere, we see a mixed picture with slightly better results in equilatitude, and we also saw kind of like a worse picture in the winter hemisphere at 20 degrees north and 800 to 1000 Kelvin of potential temperature. So unfortunately, I didn't make it to the very end to try the machine learning approaches. This is partly because downloading MR2 and MR5 takes a long time because these data are very big. So this is a step I would like to do in the next few weeks, if possible, to look at these two different models and also using the climate indices as predictors. I will leave the 4 key points here as takeaways for you, and thank you very much for listening to my talk.
Anybody have questions for Charlie before we wrap up?
I love LiDAR. Great job.
Jim,
Thank you. Appreciate it.
Jim is a big fan of LiDAR. He loves LiDAR. And so do we have one of those like mobile LiDAR things that we can carry around the building? We need to get one of those.
We should get one of those. Yeah.
They're
Charlie,
pretty nifty.
and this is kind of open to all the students too, but like, can you speak to Charlie? How did your like comfort and confidence with Python change? Like from when you enrolled in the course back in the fall of 2025 to now, like how do you feel now compared to then in terms of like your efficiency and comfort with Python?
It's a game changer. I think it's a drastic difference. I think each class sort of as individual units and as sort of a whole course has been really, really great as far as building up the skills to develop more and more interesting workflows and allow each of us to sort of pursue the things that we're interested in. I think it's super cool how different all of the projects have really ended up being. And I think that really speaks to the program, that the sort of tools and skills that we're learning can be applied in so many different directions. I think it's great.
Awesome. Charlie, Nim, I saw you turned your camera on. I don't know if you wanted to respond to that as well.
I just had a quick thought. So maybe about 6 months before the program last year, I was teaching myself how to write print hello world. And I was very uncomfortable with Python and never thought I would learn programming. And to see how far coming through the program and working on really advanced geospatial, I just wanted to say that it really did take me from a very, very beginner to, you know, doing a lot of really cool stuff. And the program was awesome.
Vivian or Nate or Max or Kaylee want to comment on like how your journey went from the start of the program to now in terms of comfort, confidence, efficacy with Python?
Yeah, I can comment. So prior to starting the certificate program, I I've definitely wanted to learn coding for a while, but I wasn't super familiar with it, and I do definitely feel like just geospatial science and just GIS in general has always definitely been the field I've been interested in, and I do feel like learning Python for this program has allowed me to expand my horizons as a scientist.
Well said, Lillian.
Yeah.
And go ahead. Hank.
I had like Jennifer gave me some stuff to work on in Python, and I was like, cool, I don't know Python, this will be fun. So this course taught me Python so that I could do my job effectively. So I really appreciate the level of like advancement in Python specifically from this course, and like I think it was a good opportunity to like really like learn some nuance of geospatial coding in Python too, like all the different packages that are available, and yeah, I learned a ton. Perfect.
I just echo all the same things that everyone has said. I don't have a lot to add, I think, but I really enjoyed working with my project partners as well. That was another great way to kind of learn together. Yeah, the whole course package really helped me with Python as well.
I don't know if Kaylee's still on or not, but she, I want to give just kind of one last plug before we sign off here. Nate and Kaylee, and Max, I believe as well, are all like employed at CU in one way or another.
Not Max.
I'm not really.
Max is looking for a job, so if you Max is about to be on the job market.
There we go. Yeah, so Max, put your GitHub in the chat.
Yeah.
If you are an employee at CU, you are able to use your tuition assistance to do all of this too. And so if you're employed here or you're I guess in Charlie's case, Charlie is a graduate student at CU. So his situation is slightly different, but I guess if you're enrolled here at CU as well, you're also eligible to take the courses and earn a certificate. And so lots of different ways that you can engage. And I want to give a big shout out to Lily. This is the first time that she's taught this course. If you've ever taught anything before and been thrown into the classroom for the first time and trying to pick up the pieces from whoever taught it before, like that's a challenge. And so she did a great job. Another big shout out to Dr. Catherine Siegel, who's not here today, but is at ESA. She helped get these folks up from, ground zero at the beginning of the fall through to a place where they could help do these big advanced projects with somebody like Lily and project partners. And so big shout out to them. Thanks to those of you that were on the call who are prospective students. I hope this was helpful to you all. I hope that you could see from those kind of testimonials at the end that you don't have to be an expert in Python to do all these kind of things. Like we really love working with beginners. And we really like to help see the trajectory that you just saw in these projects. And so I think with that, I will wrap it up. Thanks everybody for putting your links in the chat. You actually get paid. There you go.
No, I didn't get paid to take, but it only cost me
it cost you
$45. It's like
$45.
$25 to take 3 courses.
I mean, even if you do it during a workout.
Like, yeah.
Figure it out.
I was thinking to sign it up.
Charlie, great job. Thank you, Charlie. Thank you, everybody else. Livian, Nate, Max, Kaylee, Nim. Thanks, everybody. Great job.